All right, let's talk about the universal law of gravitation. To do this, we're going to first discuss some definitions. Then we're going to talk about a problem that troubled Sir Isaac Newton. And then we're going to take a look at a relationship that will help guide our thinking. First of all, our definitions. There are three key terms that are important for you to understand. First is directly proportional. Directly proportional is a mathematical term talking about how two variables were related to each other. If two variables are directly proportional to each other, then looking at it graphically, as one goes up, the other goes up also. Another way of looking at it is A is equal to B. Now, if B gets bigger, what's going to happen to A? A will also get bigger. When this happens, we can say that they are directly proportional to each other. The symbol we use for proportional is a little squiggle sign. Now, if directly proportional means that as one gets bigger, the other gets bigger, inversely proportional is the opposite relationship. Inversely proportional says that as one variable gets bigger, the other variable gets smaller. So inversely proportional would be saying A is equal to 1 over B. As B gets bigger, A would have to get smaller. Now, the third term that you need to know is gravitational constant. This big G is a constant value that we use in gravitational calculations. And we'll talk a little bit more about it. The key thing I want you to remember is that it is a constant. Whenever you see the big G in an equation, for example, F is equal to big G m1 m2 divided by r squared. This big G is a constant. There is one value and one value only that can be used in there. In some ways, it's kind of like when you see the pi symbol and you know that that's 3.14. In the same way, pi has a given value that is always used. G has a given value that is also always used. Understanding these definitions, let's go ahead and take a look at Newton's dilemma. Sir Isaac Newton was a very, very brilliant man, and he had a problem. He had been studying the work of Johannes Kepler, who established that planets do not orbit around their star in a perfect circular orbit the way had been previously thought, but instead orbited in an ellipse, which is kind of an elongated circle. Now, that they did this was undeniable. The mathematics fit the observations. But the big question that existed in Isaac Newton's time was why? What was it that caused the two objects to behave the way that they did? Now, Isaac Newton has told at least 4 people that he got his inspiration from an apple orchard. Now, maybe he was sitting under an apple tree and he got conked on the head, as some legends have it. But regardless of what happens, he saw the movement of an apple and he compared it to the movement of the moon. And he realized that the exact same forces that were acting on the apple were the exact same forces that affected the moon. In Newton's writing, there is a picture, something similar to this one, on which we have what we've come to name Newton's Mountain. And if we were to throw a ball from the top of Newton's Mountain, the force of gravity would cause it to fall down to the ground. If we were to throw it with a higher velocity, it would go further before it fell down to the ground. But if we were to throw it at, let's say, 8 kilometers per second, then as our ball traveled, it would also be falling. Now, Newton's first law says that it would go in a straight line at a constant speed unless acted upon by another force. And that force is gravity. And if we launched an object at 8 kilometers per second, it would end up falling around the Earth. Now, this was a phenomenal discovery by Isaac Newton. It helped to better explain what was causing the moon to stay in its path and the Earth to stay in its path also. He and his friend Robert Hooke discussed for many years what the relationship was between the objects. Now, it was clear that mass was a part of the relationship, but Robert Hooke said that distance also had something to do with it. Isaac Newton used his genius to create a relationship that worked to explain how these variables are related. What he discovered was that the mass was directly proportional and that the distance was inversely proportional. Now, this means that the mass of our objects, if either of them increased, then that also increased the force of gravity. And they were inversely proportional to the distance. Not just inversely proportional, but inversely square proportional, which means that if I have two objects with a known force acting between them, if I double the distance between those two objects, while the distance has gone up by 2 times, the force acting on it would be 1/4 as strong because of the squaring value. So let's take a look at some examples. Let's say that I had 2 objects and they were a known distance away from each other. The mass 1 and mass 2. What would happen to the force acting between these 2 objects if mass 1 was doubled in size? Well, looking at the relationship established by Isaac Newton, we could say that the force itself would also be doubled if one of our masses was doubled, because they are directly proportional. What would happen if our other mass were also doubled? Well, if we have both masses doubled, then the force would be increased by 4 times. What would happen if we were to decrease the distance between our 2 objects, so we only had 1/2 the distance? According to this relationship, half the distance with that squared value there would mean that the force would increase 4 times as much. Now, this is just a proportionality relationship and did not actually give a complete and final answer. In the century following Isaac Newton's death, a man by the name of Cavendish figured out what was missing in Isaac Newton's equation that would make it mathematically work. And what he did is he created a torsion balance. This is where he took basically a string with a very light rod and 2 small masses. Now, these masses could be perfectly balanced, and the amount of resistance was very, very small. So when he brought 2 larger masses nearby, he could measure the amount of rotation that this torsion balance took. And what he discovered was that there was a definite, consistent value, and that this consistent value, this universal gravitational constant, was 6.67 times 10 to the negative 11th newtons meters squared per kilogram squared. So, what is the universal law of gravitation? The universal law of gravitation says that the force of gravity is equal to our universal constant, and it is directly proportional to the product of the masses divided by the distance between those masses squared. All right, Key things to remember. 1. The universal law of gravitation applies to things both on the earth and off the earth. The universal law of gravitation tells us that mass is directly proportional to gravity. It says that distance is inversely proportional. That the equation is made true by Cavendish's universal constant, which is 6.67 times 10 to the negative 11th newtons meters squared kilograms squared. Now, this is a very, very, very small number, the equivalent of 0.0000000667. Now, that is a very small number, indicating that the force of gravity is very, very weak. The reason it has such a great influence is because it's affecting such very large objects. Hope this helped.